Thank you, Julius. Welcome. Thanks all for coming. It's late in the day, I know. Second day. It's been probably a lot of information for you all to take in. Happy that you are here. This is a talk for data scientists focusing on R and, so to speak, wondering what Spark can do for them. I normally would ask for a show of hands, but the lights are blinding me, so I just assume that you guys are mostly R people looking for answers how Spark can help you scale. What's the agenda? What we're going to talk about? A quick slide about myself, and then we're going to talk about Spark and R. And I'm going to highlight the architecture and various aspects of it, what you can do, what you need to do to make the most of running R on Spark. We're going to look at various things. And then we're going to look at tips and pitfalls. We've done a number of projects now with SparkR, and of course, this is software, which means it's not everything works as advertised, and there are still glitches here and there, and maybe I can help you sort of, at least if you haven't seen those glitches before, be aware of them and maybe take measures to ensure that your project goes smoothly. And then you might wonder what's the last point. We're going to talk quickly about Python as well. As I said, I assume we're all R people here, but just in case, we're going to talk quickly about Python, and there's a reason I will explain later why that's important. And then we're going to end up with a summary and an outlook for SparkR. Quickly about myself, I am a computer scientist, so I come more from the IT engineering side of things. I've spent 20 odd years in consulting, various industries, done mostly technology, enterprise integration, and business intelligence and data warehousing. And about 6, 7, 8 years ago, when this thing called Hadoop became an interest, it got traction in Europe, then we switched to Hadoop, and very soon afterwards to Spark, because it was quite clear to us that Spark would become but essential player in the big data ecosystem. I've been a speaker at Spark Summit and Hadoop Summit and other meetups in the last years, and I'm the founder and CEO of Wireframe, and this is my shameless plug here now, we're doing consulting, but we're also having 2 products. One is Pattern Finder, one is Pattern Generator. Pattern Finder is a tool for what we call business machine intelligence, sort of a data warehouse for machine learning. I mentioned this because this is built heavily on SparkR and partially PySpark, and we're going to reference some insights we gained during the implementation of Pattern Frame. If you want to know more, the URL is wireframe.digital. Check it out if you're interested. SparkR Architecture. This is not a standard slide you're seeing here. This is just a sort of a reassembly of the components to put it in a way that I think makes sense and is easy to digest for somebody with a data science background, highlighting hopefully the important aspects of Spark for you. And I think you can sort of partition it in that way that we see Spark. The very core of Spark is obviously a distributed framework, which means it allows you to run computation and process data on a number of machines. That's symbolized in this blue layer with these machines. That's what Spark at its very core is. It also gives you access into a data lake. We're going to talk about this in a minute as well. It's very important, has implications which I think will be important going forward. Rolling out more and more R applications on SparkR in production in large organizations. So this is the very core, accessing data in a data lake, getting them into memory, and then have Spark process them. Spark comes with a set of libraries, very powerful libraries, which give you additional capabilities, such as a SQL library, streaming, machine learning, GraphX for graph processing, and that's the very core of Spark's library. And on the very top, you see 2 packages. I put it in place for the discussion later on for Python. There are 2 packages that integrate with Python and R, which are called SparkR and PySpark respectively. And those give you the option to to integrate with, run basically R and Python applications on your Spark cluster. And that's the essence of what we're going to talk about now. As I said, the very first thing is you have to get access to data. And how does Spark give you access to data? Well, obviously, Spark doesn't deal with persistence per se, but has an interface layer and relies on a persistence layer that provides data. And that could be normally now an HDFS in a Hadoop cluster. It could be blob storage on a cloud layer like AWS S3 or Azure WASB or Azure Data Lake Storage. And Spark reads data from that storage layer and distributes it across the nodes in memory and provides you with what you see on the screen here with this data frame box. This diagram is slightly misleading, and I think most of you are aware of that. This data frame box is actually, there's two types of data frame. The first one that you would see would be the Spark data frame. So when you within SparkR instantiate a data frame that is read from HDFS, what you get back is a Spark data frame, which is nominally using the same name, but technically, completely physically very different implementation. That's literally a distributed data frame, data spread across all those nodes. You can apply, we come to that later on, a command or function called collect, which will then retrieve all that and merge it onto a single machine and give you literally a native R data frame, which is the object which you are all probably very familiar with. So that's the distinction just to keep in mind. We'll come back to that. It's going to be, going forward for SparkR's future, it's going to be very important and very relevant, this distinction. We're going to talk about this in the second half of the talk. This, what I'm just talking about, retrieving data, is obviously nothing new. That's something I suppose all of you are aware of. What I'm not so sure that people are aware of is if you're looking at this within a large organization, data scientists are very often not completely aware of how the traditional IT department works. You have to be mindful that security is a huge priority for IT organizations, which means when I go and talk to data scientists, I'm always slightly amused, let's say, because they're doing good work and highly sophisticated work on data, but the data very often is in a CSV format, and it's literally a file residing in maybe a shared file store or somewhere, which means you have very limited control over safety and integrity of the data set and who accesses that. And this is something to keep in mind going forward, which I feel will be very important in the future. If you're using Spark as a layer to integrate with the data store, the persistence, you get access to things like data security and governance. Being European, you can imagine that recent introduction of GDPR raises a number of issues for our clients. And those tools are available in the big data ecosystem that give you ready solutions for that, which allow you to make sort of control who has access based on role-based access control models or attribute-based access control models. You can track the lineage of data, so you know exactly where data is coming from, how it's being transformed, and so forth. So basically, Spark is functionally not a big deal from a science perspective, but the IT department will want to have a handle on that to ensure that we're meeting the guideline requirements from compliance and regulatory requirements possibly. As I said, the libraries on top are things like SQL, which Carl just showed in the talk, in the preceding talk. I was very happy to see that because I had thought that this should be a no-brainer, but I think very often data scientists are slightly reluctant to use that API. I'm not quite sure why that is. Maybe it's because SQL is a slightly different animal. I'm not quite sure, but as Kyle just showed, it's very easy to use from SparkR. You can really just naturally mix SQL code in your Spark code and have it executed. The reason I mentioned this also, why it's important from us, if you want to look at this more strategically, is we're all probably, I don't even need to ask for a show of hands again, it's quite common knowledge, or a solid heuristic, let's say, that feature engineering, what's called more like ETL in IT, in the classic IT world, takes a lot of work and should not necessarily be part of the data scientist. The people we're working with, our clients, have occasionally our applications in the range of 20, 30,000 lines of R code, but they're all telling me, not so secretly, that probably 2/3 are feature engineering and data preparation code, which they would actually like to get rid of. So SparkSQL would be something that can be very helpful in that respect. The next thing is quite important. This is Spark MLlib. This is now not the only, but a central tenet of SparkR, which are Spark's built-in machine learning libraries. And the thing that's so special about them is those functions, those methods that you get from the library are natively developed in Spark, which means they are actually out of memory / scale out methods. They're able to process, I use the word arbitrarily, but to some degree, arbitrary large data sets. So you can really do a lot more than you were able to do before if you're looking at a pure single R server application. We're not going to spend too much time on that. This is not actually even the up-to-date version. This is Spark 2.1, I think, what you see on the slide. So we have now, I think 2.3 came out in February or March. So there might be already an update with new methods added. So go and check that to see what's the latest set of functions that are supported. The next thing is streaming. To be very honest, we haven't built this in production yet. We have done a prototype so far in streaming. I mentioned this. I'm not quite sure how relevant it's going to be going forward, but I mentioned this. This is sort of a for free that you get as an R developer, and it can be potentially quite cool. This allows you, Spark gives you the option to deploy streaming applications, which means you get data coming in motion, and what Spark will do, it will add it to the table and run your code on that table. Conceptually, it's quite straightforward, not really complicated. Technically, the implementation details behind it are quite intricate and really clearly not trivial. But the bonus is, for you as an R programmer, you can plug R code in a streaming application, which would be, if you have that requirement, which would be a very, very difficult thing to do in any other way. And the last thing is SparkR UDFs. Now, I mentioned this because we're doing a lot of that, a lot of work with SparkR UDFs, and I'm not quite sure if the reason it's worthwhile to point it out is that I always get the impression that those APIs are not necessarily that well understood. So I'll take a minute to go through that and give you a sense of what they're doing and what they can do for you. SparkR UDFs, there are 3 basic types. It's gapply, dapply, and lapply. Lapply is somewhat of an outlier. I'll cover it quickly in the next slide. The important 2 versions are gapply and dapply. What they do for you is, you see on the left-hand side, you see this orange box, and that's supposed to be a Spark data frame. So imagine this is a logical representation. It can be an arbitrarily large data set spread physically across a number of machines. And what gapply and dapply will do for you, you give them a data set and you give them a function, and Spark will then go and run that function on each node in your Spark cluster. That's what you see in the middle. Those gray boxes are supposed to be physically workers or nodes, boxes in your cluster. And you see this Spark little icon. The Spark icon is the Spark executor that holds your partition, the part of your data locally on that machine. And what it will do is that it will then transfer that partition, that local partition, into your R process, start an R process, and transfer data into your R process and execute your R function locally. Your output has to be an R data frame. That's what you can see at the very right-hand side in the gray box. That's an R data frame. And what Spark then will do, it will transparently, no work required from an R programmer, take the R data frame and merge it back, convert it back into your Spark result data frame. Again, that's the right-hand side, which means an out-of-memory scale-out data set can be arbitrarily large. There's this approach, we're going to talk about this a bit more in the next 2 slides, is important if you have parallelization where you want to do the same model potentially on different data sets. I'll talk about this in the next slides, what use cases would be for that. If you want to do that, what's important is the distinction, to understand the distinction between dapply and gapply. Now, dapply, very careful. Dapply does exactly what I just described, but it does it on the standard Spark partitions. In case you're not familiar with that, just a couple of words about this. When you read in a data set and it's large enough, Spark will distribute it across the nodes in your cluster. So you will have distributed data frame. And the step of assigning or breaking up your data in chunks, which are called partitions across your cluster, is called partitioning. You can influence that, but you don't have to. But if you don't do it explicitly, then you have no control over what dapply will actually do for you. That meaning, like, you could have skewed data, you could have one partition that potentially would be very large, it won't be not so large, etc. So you would have also no control of actually what your function is going to process, because your function could process any set of, be more precise, any subset of your data. It can work in certain situations. The easier approach is to use gapply. Gapply takes as input not only your data frame and your function, but also one or more columns. And those columns are partitioning parameters. That's exactly what then Spark takes in. And before it executes your R function, it does a shuffle, which means it rearranges the partitions across the Spark cluster based on your columns that you specified when invoking gapply. And then you have exact control. You can, for instance, have a column which would say country. And if you do a gapply, then you would know that your function only processes a data set per country individually. There is a version called lapply, which takes an R list and returns an R list again. I would say the applicability of that method is a bit limited in my opinion, but it's there for sake of completeness. We just spoke about big compute and UDFs, what they can do for you. We're seeing actually a number of use cases. They're not talked about that often. They're not that widely discussed, but back home in our clients we're talking to, we see this actually in a number of places. So we see one case is one client does time series analysis, and they're doing first a number of time series, and then per time series they're fitting a large amount of models, averaging them, sort of an ensemble learning, and then do some model selection. There's a lot of computation going on in parallel for a number of time series. Stuff like things like hyperparameter sweeps. If you're not sure which hyperparameters to use, you can do this in parallel. One thing is, as I mentioned, our own product pattern finder, which does exactly that. It takes the data warehouse input and sort of explodes it into all subsegments and fits models for each individual segment. We're also doing things like for IoT data, shape and what we can also call motif detection, like that would be irregular time series. You're not looking for things like seasonality or trends necessarily. You're using more like little individual motifs or shapes within your time series that could be correlated with machine failure, for instance. We have not yet reached a point where our analytical capabilities are so high that we can do this with just applying a simple formula. This is, to some degree, a brute force approach, to be very honest. But that's exactly where Spark comes in and helps us just fantastically. And of course, things that have also been around for quite some time, like Monte Carlo simulation. If you have just 2 clients of ours, one in finance, one in manufacturing, different problems, value at risk on the one hand side for finance and inventory optimization for the manufacturing people. But from a parallelization point of view, conceptually the same problem, what we're doing is we're distributing, in the one hand, portfolios of financial instruments, on the other hand, products, items, with their stock and inventory levels. And then we're applying parallel computations to either optimize stock parameters or compute value at risk KPIs for given market scenarios. And that's, these are things that lend themselves to for instance, to do with SparkR UDFs. To put some numbers on that, that's very interesting as well, because this literally can unlock new applications for you, because they were just not computationally not feasible for you. They were just taking too long, and as a consequence, very often they're also too, maybe prohibitively expensive. So just two things which are quite interesting. One is a real-world example from our clients. Time series forecasting had developed their own R application, and that maxed out at 22 hours runtime. And that was not the end of it, actually, in a sense that the application was supposed to process much more data going forward, and that was clear that that would be not acceptable. And it's also probably hopefully an interesting insight for our developers. What the team did was try to parallelize themselves with an R package. And it worked. They brought it down to 4.5 hours. The problem was it increased the complexity of the application massively, and they had to, of course, look into things like parallelization like themselves, which detracted them from doing the data science work, and added a lot of headache on the engineering side. And we then moved this to SparkR in a cluster with 25 nodes, and we were able to run this within 12 minutes. So that was a nice win. And that's not the end of it. We're continuing to cut runtime here, so that's good. For Pattern Finder, which we're using for a different client, if we're doing things like for multi-million data market segments, some model fitting, and just do a back of the envelope calculation here, but just gives you an idea what we're talking about. For 15.5 million models, and I think this is based on a random forest, I'm not quite sure. And we're assuming 1/10 of a second for fitting, for training the model, and also testing the model, and doing I/O work, to be honest. If you then multiply that, you'll end up with around about 18 days if you run this sequentially on one single server. And if you run it in Spark with the help of UDFs I just described, with 1,000 cores, you should end up with something like 25-30 minutes roughly. This also brings into play another aspect which is quite nice. If you're able to do this in the cloud, that is economically then very, very interesting, because that allows you to scale your resources according to these burst and peak loads that you're going to see in that sort of applications, because you're not using 1,000 cores or 250 machines, whatever, over an extended period of time, but rather for half an hour, and you can scale them down, tear them down, and obviously no costs associated anymore with that. The implication, what's important is, I think, for you to use this, is just familiarize yourself with the R UDFs and the parallelization model. Beyond that, there's not much to do. We've seen so far that people were always surprised that with relatively little code modification, they were able to leverage Spark capabilities. So that's my motivation here. Tips and tricks falls. We're quickly going to go over it. Time is running short. If you're using UDFs to do computations, very often what you probably will do in R is generate diagrams, binary output, and that's something that you cannot easily do out of the box as of yet. If you produce a PDF or PNG, JPEG, what have you, this is not yet supported to store that back out of the box with the Spark data frame. You could, and you need to currently do it and serialize it some way yourself, and then either you store it in shared storage like HDFS cluster storage, or S3 or Azure blob storage, or you serialize it and put it in a data frame as a sort of a byte stream. That would be an option. I just put it in for completeness. There is a JIRA, Spark 21866, I think, which says image support now added. That is not the answer for this question. The intention of that JIRA is to make it easier to train deep learning models and feed them via Spark with binary input like images, for instance. I just mentioned it. This might be going forward something worth to look into, maybe hook into that API and use that to return your images to Spark. And similar to that, the same thing goes for if you have trained an object, a model on your node. What you normally did probably was call save RDS and store it as an object locally. That won't work within Spark as well. Again, you'd have to find some alternative, like potentially you could serialize it as JSON and then stuff the JSON object into your Spark data frame. That would be a way out. This is something that already exists in Spark MLlib. If you train a Spark ML model, then you have, of course, the option to store the model via normal standard API. Then there's things like if you want to run R on a Yarn cluster, but it's not installed. There's a link on the slides, you'll find on the slides, which gives you a PDF. If you still, that was 2 years ago, if you still have the need, that should still work, give you, I don't know, 2 hours. Within 2 hours, you would have your own custom build of custom build Spark and be able to run our SparkR on a Yarn cluster without having any R installed. Mixing Scala and R is not supported out of the box. If you do submit to the cluster, Oozie, if anybody's using Oozie, that's a Hadoop tool to orchestrate Hadoop workflows. Oozie has a Spark action, but that doesn't work for SparkR, unfortunately. Can be replaced very easily with a Oozie shell action, so that's not a big deal. And if you have the need, if you use Apache Livy, Livy is, in case you don't know, is a REST API that helps you submit Spark jobs remotely. We found out very much to our dismay that this only supports, Livy supports only Scala, Java, and Python. Dare I say it, Python. Which brings us to the next question, and what about Python? So we have 3.5 minutes, I'll quickly go through that. The reason I'm mentioning this is, I would say to our surprise actually, we found out that wherever we go, we meet a lot of our people are very happy and they're very keen about knowing about SparkR, and there's a great deal of potential there going forward. But wherever we go, we get the question, secretly or not so secretly, what about Python? Do I have to learn Python now? And we're going to quickly look at that now. Programming languages wars are nothing you should get into. So this is, I'm trying to stay away from that. But we found it very interesting that it looks like a dichotomy. People are mostly focusing on R or on Python. And we felt like add some data points around that to see where this is leading. So if you just quickly compare R and Python, both are interpreted languages. R dates back to 1993, Python to 1991. Both have, the bottom line here is both have they have powerful and they have large libraries, so there is no shortage of functionality. Usually you'll be very happy to find a number of methods, or very often even alternative methods in each language as reservoir. Both come with a nice package management system, so it makes it very easy to add new packages or libraries. And in terms of IDEs and development environments, you have stuff like PyCharm and Spider for Python, you have RStudio for R, and there is the new set of notebooks that have become very popular in the last years, and most of them also support. Here it's, to be very honest, things like Jupyter, very, very popular, is Python-based, it comes from the Python world, but also lets you access and execute R code. So there is a slight bias towards Python, but you are free, nothing keeps you from using R there as well. What else do we have? We have 4 more aspects we looked at. One was market momentum. Just thought this might be very interesting as well. There are 2, we looked at 2 market researchers. One is a company called Redmonk, the other one is this Tyobe index, and both come back with the same result. The results date to January and the other one from May 2018. Bottom line here is just there is a great deal of attention going into Python, but R is not trailing far behind. And if you look at the whole landscape, you'll see that both actually are very, very popular languages. If we wanted to do some programming language wars, I could even argue that Python is more widely accepted because it's also somewhat of a more general purpose scripting language as opposed to R, which probably is more suited to quantitative modeling and statistical computing. Deep learning, that's something where we have to say there is a difference. The deep learning, this is just a subset. There are more obviously out there. Those are just very popular ones. Deep learning frameworks very often come with actually almost by default, it seems nowadays, with a Python wrapper. R is not so well supported, but Keras, a very, very popular API. Also, there is from RStudio a package that allows you to access Keras from R, so you can do and use it from R as well. If you look at PySpark and SparkR, you'll see that actually functionally, those are, they have access to, this is a very broad statement and drilling down in detail is different, but they have more or less access to the same functionality. One difference, I know I'm over time, but I'll close in 30 seconds. One difference is architecturally, you've seen this, maybe if you've been to one of those talks, it has been mentioned today and yesterday already. There's one fundamental difference. Spark is a JVM-based environment, a Java virtual machine, and R is running its own process. But the same applies to Python, by the way. So we have to use Python, and when you use R within Spark, you have to cross this boundary from the JVM into the non-JVM world. And that gives you headaches and low performance and is certainly less than ideal. Good thing is, and I want to highlight this, I'm not quite sure if it's going to fulfill its ambitions, but we have a project called Apache Arrow, which should come up, strives to come up with a shared memory format that will, in the end would make R use the same memory format as Spark and as Python, which would lead to sort of an interchangeable way that you could mix and match your applications. As a summary, we strongly believe that Spark is the best option to scale R. That's a very broad statement. There's also two other options you would have, Spark+AI and Microsoft's R server for Spark. But using Spark to distribute computation with R is probably the unanimous judgment is the best option. There's other things as well, security we mentioned, and Arrow. But I think the outlook is, if Arrow fulfills its ambitions, we should end up with a very open data science runtime / platform, which is Spark, and you can equally run R and Python on top. And having said this, the last slides were meant to sort of address those concerns. Nobody will stop you from learning Python, but there is no need for it if you are an R programmer. There's a lot you can do with SparkR and leverage all the capabilities. And with that, I say thank you very much for your attention.
Thank you, Heiko. We're a bit over time, so we can take any questions offline with the speaker.